So now we will have Eric Cavalcanti talking about local friendliness. So you have 20 minutes plus 5.
Thank you. First of all, of course, I would like to thank the organizers for a very interesting conference and it's truly paradigm challenging, that's for sure. And let me first, secondly, acknowledge my collaborators in this work. First of all, the one who did all of the hard work, which is Aníbal Utreras Alarcón. He's a PhD worker of Howard Wiseman and I. Yongchang Liang helped with the theory part. He's in Taiwan. And the others are members of Jeff Bride's experimental group at Griffith. I also should acknowledge funding from the ARC and from the FQXI. Now, local friendliness. Although I've lived in Australia for 15 years, I'm originally from Brazil, so I'm kind of local. I think I'm sort of friendly. But that's not exactly the kind of local friendliness that I'm going to talk about. Of course, here locality, local means locality. And friendliness refers to Bigness' friend thought experiment. And I'll talk about a work that's building upon some recent work from Charles Love Bruckner, which is an extension of Bigness' friend to a bipartite setting, and that's where the locality comes in. So first, as a motivation, am I too far from this? Can I have some tech help on this one? Oh, I did turn it on. Is that another place where it needs to be switched? No. Nope. Can you hear it? Maybe needs to be on the. Yeah, maybe that thing being on top is not helpful. Maybe just.
Okay.
Okay. So, as a bit of a personal motivation for what why I'm interested in this, I'll start with a quote from Bell, who said, "For me, then, this is a real problem with quantum theory: the apparently essential conflict between any sharp formulation and fundamental relativity. It may be that a real synthesis of quantum and relativity theories require not just technical developments, but radical conceptual renewal. In my opinion, this conceptual renewal relates to our concepts of causality, much in the sense that Don was talking about in his talk. Now, in terms of, if you think of the classical, of the causal implication of relativity as being just no signaling, then Bell would have said this: do we then have to fall back on no signaling fast and light as an expression of the fundamental causal structure of contemporary theoretical physics? That is hard for me to accept. For one thing, we have lost the idea that correlations can be explained, or at least this idea rates reformulation. Again, as Dom very helpfully already discussed in detail, that the classical formulation of causality can traces back to Reichenbach, and in a more modern version to Pearl's formulation in terms of direct acyclic graphs. And from that we can derive the Bell inequalities and a contradiction with quantum mechanics. And would also mention that we can also do a similar thing for Kochen-Specker contextuality. That's a recent paper of mine where I showed that we can also understand Kochen-Specker contextuality as a violation of classical causality in this sense. So then this means therefore that this framework is wrong, it's false, but it is very useful. After all, it underlies what in many fields of science we understand by the idea that correlations do not imply causation, for example. And a very interesting program that tries to resolve this problem is this program of quantum causal models that Don was talking about. This is perhaps not completely exhaustive list, but there's a number of different proposals for quantum causal models that attempt to solve this problem, which I call the easy problem of Bell, which is the problem of explaining quantum correlations causally, to give a causal explanation of quantum correlation, which generalizes to the quantum case, but also contains the classical case as a special case. Why is that the easy problem? Now, in the rest of that quote that I put from Bell, he said, more importantly, the no-signaling notion rests on concepts which are desperately vague. The assertion that we cannot signal faster than light immediately provokes the question, who do we think we are? And here, of course, Bell is talking about the measurement problem. That's what I would then call the hard problem of Bell. And quantum causal models, they are still based on an operational description of quantum mechanics. And so it remains to be solved, the second part of the problem that Bell had with an alternative to his formulation of local causality. I gave a bit more detail of this argument in this recent paper here. Okay, so then that brings us to Bigness' friend paradox. I think the interesting thing about paradox is that they force us to really sharpen our intuitions about certain problems. And perhaps the quintessential intuition pump for the measurement problem is Bigness' friend. There's a couple of recent results that have extended Bigness' friend setup. So Bigness' friend, if you don't know, is essentially Schrödinger's cat, but with a friend inside the box instead of the cat. And a couple of recent results have extended that to a bipartite scenario, which allows us to prove some no-goal theorems, bringing in some assumptions like locality. One that is very discussed recently is this one from Florianopolis, but it's not theory independent, and so I find it a bit less interesting than another one which has not been commented so much, which is this recent result from Bruckner. And that's what I'll base this work on. It's on this paper that was published this year in Entropy. And so the scenario is one where we have Charlie and Debbie sharing an entangled state in two separate labs. And looking here, at Alice and Charlie, Alice is to Wigner as Charlie is to the friend in this case. So Charlie is put in this hermetically sealed box, which of course shields it from the coherence with the external environment. And Alice has, in principle, full coherent control of the contents of the box, including Charlie and the system that Charlie is in possession of. And Bruckner's proof then is based on the possibility that Alice may open a box, well, Charlie and Debbie will perform a measurement on their subsystem in this entangled state, only a single measurement. And Alice may choose to open a box and ask Charlie what he observed, or she may choose to perform a measurement in another basis, which includes Charlie and the system and everything inside the box. Of course, it's very hard to do that, but in principle, there's nothing that stops us from doing that if quantum mechanics is universal and applies to even a large system like whatever's inside that box. So I'll just skip to the statement of the theorem from Bruckner. It's the following. The following statements are incompatible. First, the universal validity of quantum theory, which is the assumption that quantum mechanics holds at any scale, including describing the laboratory and everything that's inside, even if there's an observer inside. The second is assumption of locality, which is that the choice of measurement settings of one observer has no influence on the outcomes of the distant one. And here I'll emphasize that this is not the same as Bell's notion of local causality. This is just what is sometimes called parameter independence or setting independence. Bell's local causality would have would be this, plus an extra assumption, which is sometimes called outcome independence, which is that the outcome of one observer has no influence on the outcome of the distant observer. So you need those two to get Bell's local causality. Freedom of choice has the same meaning as in the usual Bell scenario. And the new assumption here is this one of observer-independent facts, which is essentially that whatever is happening inside the box, the actual observed outcome of the friend inside the box has a reality. We cannot assign a truth value to a proposition about that outcome. It has an independent reality. And I emphasize that it's the actual observed outcome. It's not all the physical properties corresponding to all the counterfactually potential measurements that the friend can make. It's the one that in a given round the friend has actually performed. That's what the assumption is saying. Okay, so this is the setup that we use. It's slightly different from the one used by Bruckner, but just because it's a little bit simpler to state and also to do an experiment on. So Charlie and Debbie, as I said, they share an entangled state, and then they go inside this very nice closed box. And the protocol says that they will perform a measurement on their subsystem at some stage. Charlie will encode the outcome of that measurement on a variable C. Debbie will encode it on a variable D. And now Alice has a choice of performing a measurement on the laboratory. The choice of setting is encoded on a variable x. If x equals 1, then that corresponds to Alice just opening the box and asking Charlie what he has observed. And so she will then encode that outcome on a variable a. So she will ask, what did you observe? And assign a, the value of the observation by Charlie. If on the other hand, Alice chooses another setting, different from 1, it could be any number of settings, then she will do the following. She will perform an unitary time reversal of the evolution of Charlie and the system and everything inside the box. And that's very hard to do, of course, but we're assuming that Alice is a super observer with full coherent control of the contents of the box, so she can do that in principle. And so after that, Charlie and the system will be back to the situation they were before, where now the system is again entangled with the distant lab, and in particular, Charlie's memory of ever having measured anything is gone. And now Alice can just get the system and perform some other measurement of her choice on that system. Okay. And the other measurement settings are in 2, 3, and however many she may want, and she will encode those outcomes in a variable a. And in the other lab, there's Bob and Debbie, and likewise they are doing the same things. And Bob's choice of setting is y, and corresponding outcome b. Okay, just get some water. All right, so Bigness proceeded by then claiming in the paper that assumptions 2, 3, and 4 together account for the existence of a local deterministic model for Alice's and Bob's measurements. And in particular, in the scenario of 2 settings and 2 outcomes per party, that leads to the CHSH inequality. However, this is not quite right. Whereas the statement of the theorem is correct, the proof was incomplete. And their assumptions do not lead to a local deterministic model, they lead to a larger polytope, as I'm going to show you now. And that's already when you include one more setting. When you have 3 settings on each side, then we see a difference between those 2 polytopes. So let's fill in the gaps of the proof. So first, the assumption of observing independent facts implies that there is a well-defined value for all the actually observed outcomes in each given run, so that is conditional on the choices of setting x and y. A, B, C, and D, which are all the observations that have been done in that particular run, have a well-defined value, so therefore there is a joint probability distribution for them. And if we sum over the outcomes of C and D, we get the marginal for the observed probabilities for Alice and Bob. And of course, we want, but for consistency, that A1, that is the outcome of Alice when x equals 1, is equal to C, which is the outcome of Charlie, and that's just by construction. And likewise for B1. The assumption of locality is what we call the parameter independence or setting independence in this context. And this assumption that the outcome, say at Alice's side, does not depend when conditioned on CD and XY, and CD here are playing the role of the hidden variables in a usual derivation of a Bell inequality, then the outcome at A doesn't depend on the choice of setting Y, the distance choice of setting, and likewise for B. Freedom of choice, again here C and D are playing the role of the hidden variables, so this is formally equivalent to the freedom of choice assumption of Bell scenario, that the probabilities for the C and D are independent of the choice of settings. And the assumption of universal validity of quantum theory doesn't play an actual role in deriving the inequalities. It just plays a role the same as in Bell's theorem, which is to assume that there is a violation according to quantum mechanics. But we derive the inequalities only from these three assumptions, which have nothing to do with quantum theory. Okay, so after a little algebra, we get this situation. For when x equals 1, I keep pressing the back button. When x equals 1, A by construction is equal to to C, and so we get a model of this form. The joint probabilities for x equals 1 and an arbitrary value of y factorize in this way, where now there's a delta for A and C, and likewise when y equals 1 and b equals g, and we have the corresponding form for this model. But when we have any other values for x and y, we cannot say anything about the term that goes inside here, except that it's a no-signaling, a pointing to no-signaling polytope, and that comes from the assumption of locality. But it's an arbitrary correlation between A and B, as long as it doesn't allow for signaling between the two parties. So you may see now that what are the extreme points of this polytope? They will be each extreme point will have a well-defined value for A1, for the value of A when x equals 1, a well-defined value for B1, and it will be an extreme point of the no-signaling polytope for the remaining variables. If there's three settings per side, then there's 4 remaining variables, and there will be a point in the no-signaling polytope for those variables. So those are the extreme points. So schematically, geometrically, this is the relation between these polytopes. That's a local deterministic polytope, the local polytope in blue. The polytope that satisfies these assumptions that we call local friendliness correlations include the local polytope, but is strictly larger than that, and all of them are included in the no-signaling polytope. And with the knowledge of the extreme points, we can characterize that polytope, calculate its facets, and we have these classes of inequalities. Each one of these, here we are assuming now that the outcomes are plus or minus 1, just as a convention. And each one of these classes generates a set of inequalities by permuting the outcomes and permuting the settings for the 2 and 3 settings, but not the 1 because there's an asymmetry between them. And so there's 2 new inequalities which are not Bell inequalities. They're not tight facets of the local polytope, these 2. There's 2 inequalities which are tight facets of the corresponding 3322 polytope. There is what we call the Bruckner inequalities, which are the CHSH when we have one friend on each side. One of the measurements corresponds to the friend's measurement on each side. And also interestingly, there is one when there's also already only one friend but not 2. That is also a facet. That means that it really just need one laboratory with a friend to demonstrate the inconsistency. And importantly, the CHSH inequalities which do not include a friend, they're not a facet of this polytope, of course. Okay, so this is the experimental setup. We made an application to put a professor inside the lab, but that was denied by the ethics committee. So we have a friend, which is a very small friend, and in fact this friend has only 1 bit of memory. Not a very interesting friend, not much conversation to be had. So we start by preparing an entangled state and send of photon polarization, send 1 to each lab. In Alice's lab, the friend's measurement is realized by entangling a path that the photon takes in this apparatus with the polarization, with a polarizing beam splitter. If Alice wants to ask the friend what he has observed, Alice wants to ask Charlie what he has observed, she can put a mirror here, the dashed lines, an optional mirror that she can put there, and deflect the photons and measure the path. There is measuring the contents of the friend's memory. If she wants to perform one of the other measurements, she will reverse this evolution, reverse the entanglement between polarization and path, and perform some other measurement on the polarization degrees of freedom. And the same thing at Bob's side. And so we use this state with probability mu. We prepare a singlet state. with probability 1 minus mu, we prepare a mixed state. It's not a maximally mixed state for experimental reasons that are not important to mention. And the measurements are performed on the xy plane and schematically represented here. And we look at for the violation of this new inequality, which was the first one in the classes that I mentioned before. And so this is what we hope to see. The experiment is underway. I think I just got an email today that I might have the results. These are the theory results. So as a function of mu, this represents the value of the left-hand side of the corresponding inequality, and they are violated when it's larger than 0. So we see at first a violation. So each one of these are the first inequality in its class that is violated as we increase mu. And so we first see a violation of a Bell inequality, which is not a facet of the new polytope. So from here to here, from here on, the state is non-local. Here we have a violation of the first facet of the local friendliness polytope, which is a semi-Bruckner inequality. So between here and here, the state is non-local, but it still has a local friendliness model. It doesn't violate the assumptions that go into the theorem. And then after that, we see the violation of one of the new facets, one of the new inequalities that we derived, then a violation of one of the Bell inequalities for that scenario, which is also a facet of LF, and then finally the violation of the Bruckner inequality. So here it shows, this region here in particular shows that the new polytope is strictly larger than the local polytope. After Howard presented this talk at a conference recently, he was pointing out to us that actually this polytope was studied in another context by Eric Woodhead, which was a PhD student of Serge Massat and Stefano Pironio. And he has an information theoretic motivation for it, which is the sets of phenomena for which randomness cannot be certified device independently in the presence of an oscillating adversary. So it's interesting that he has this other interpretation, but we independently found these polytopes from this foundational direction. So what does it mean? Of course, Časlav chose to emphasize the violation of the fourth assumption, but technically what the theorem means is that one of these four, the conjunction of these four leads to a contradiction. And it turns out that for any one of these assumptions, there exists some interpretation that will keep it, and there will exist some interpretation that will drop it. So here I have an example of some of those. I won't get into too many details about each one, just mention that the question marks relate to perhaps some ambiguity about what the interpretation says, and the asterisk in the cubism/relational is to emphasize that the sense in which quantum mechanics is universally valid in these theories is not in the sense that one might think that there exists some universal wave function describing the universe, but in the sense that any agent will use quantum mechanics and to describe the potential probabilities for outcomes of observations. Now, this is an interesting point now. What's the relation between this theorem and Bell's theorem? So it turns out, as I was saying, that the notion of locality that we need is weaker than Bell's local causality. So to derive Bell's theorem, we need an extra assumption, the assumption of outcome independence, or the assumption of determinism, which implies outcome independence. So if you were one of those that thought that maybe the way in which you accommodate Bell's theorem is by dropping outcome independence or determinism, then you learn something new. You actually need to give up one of these other assumptions. So perhaps if you were going down that route, now you need to think about observer independent facts being violated. So just to finalize with some open questions first, are any of these inequalities, the new inequalities that we have derived, which are not facets of the Bell polytope, are any of them relevant in the sense that there are quantum states and settings which, for which they're violated, but one of the facets which are also Bell inequalities are not violated? And also, how large must this friend be? Our friend was a very boring friend, and we really think of that just as a toy demonstration of the of the experiment, you don't take it seriously as representing it, as you know, because it doesn't seem very plausible that the assumption of observing independent facts applies to the path that a photon takes in after a beam splitter, of course. So how large must this friend be so that this is a convincing demonstration? Is it about size? Oh, sorry. Okay, I'm almost done. Is it about size, or is it about some kind of structure or functionality? Can we ever get to that level? And I think one of the motivations for this kind of work, I think, is to give us, even though the experiments are very far away, is to give us sort of a sandbox in which we can ask these questions and try to formulate them in a precise manner. So thank you.
Thanks, Eric. So we have time for one question. No? Okay.
So that assumption about universality of quantum mechanics, or whatever it's phrased like, does it mean that everyone applies, like, what systems do people apply quantum mechanics to? So I haven't read Czeslav's paper, but I have read Renato and Daniela's paper. And one of the contentious points is that everyone says, well, I'm classical and the world around me is quantum. Whereas if everyone says the whole universe is quantum, no contradiction arises in the other paper, but I'm not sure about this one.
So you're talking about you said you read Renato.
Yeah, but not Czeslaw. So I wanted to know whether similar issues arise or not.
So here, in a sense, you can forget about that question, and it becomes like Bell's theorem. It becomes an experimental question. You can, in a sense, there is no assumption about quantum mechanics in this theorem. You derive an inequality, and if the inequality is violated, and that's an experimental question, one of the other assumptions, not the universal validity of quantum theory, will have to be false. The universal validity of quantum theory just tells you that Alice and Bob could in principle perform that experiment, and that's what they would observe. But it's just about what the observations would be. It's not about whether they would use collapse and how they would, none of that matters. And so in that sense, I think it's more interesting than
okay,
talking
cool.
about it.
Thank you.
So let's thank Eric again.